All right, folks, let's pick up with where we left off with yesterday. And so I hope that you were able to go through this particular graph here and interpret the information that was taken from it. And you were able to understand how we go about obtaining that information about the movement of an object based simply on some lines on a graph here. Okay, so we practiced that yesterday. But the 3 or 4 of you weren't able to draw, submit the work, please make sure you get the work submitted, folks, because I did ask you to give me some samples of your interpretation. Remember yesterday what I left you with is that I asked you to pick one of these 4 objects here. So we have 4 objects whose motions are represented here on this graph here. And I asked you just to pick one of those lines and show then how the object is moving. And so please make sure you get that done. I understand that there's a lot of things going on, but and I've been fairly lenient with accepting the work. But please make sure that you submit the work and get it done and in the form that I asked for at the very beginning of this time that we started our online learning. Okay, so please make sure you get that done. But quite a few of you turned in very good work, and I'm going to go ahead and share that with you with everyone today, and then we'll use those to interpret these lines as well. Okay. All right, so yesterday we left off with this graph here. So I arbitrarily just chose A. I chose line A, and in line A then it represents the way that an object moves. And so with that said, then we saw then that since the graph here, the line here it has a negative slope then, what we're saying then is that the object is slowing down. Okay, it's slowing down because it starts out at a certain velocity. And we had arbitrarily chosen here at times equal t0 is equal to 0 seconds. At times equal to 0 seconds, it had a velocity of 10 meters per second. Okay, halfway through the motion, we said then, and we arbitrarily called this one, okay, t1, which is going to be we arbitrarily said it's going to be 5 seconds later. 5 seconds later, then it moves at a rate of 5 meters per second. And then finally, then we said at this time here, which is, well, I think we just said 10 seconds in. Okay. 10 seconds in, E is equal to 10 seconds. Okay. It reaches a final velocity of 0. Okay. All right. So with that said, then, my question to you was, hopefully, first of all, you recognize then that that's what we have here. I asked you to find then the accelerations if we are given this information here. Okay, so this object, remember, even though this object is moving in the graph here is a negative slope, what we see is that the object is actually moving in a straight line. And so therefore we can calculate for the acceleration to make sure you're able to do this, because we'll talk about this in just a moment. Okay, and we can calculate for the acceleration if we know what the change in velocity is over the change in time. Okay, which is going to be then v final minus v initial, the instantaneous velocity at the time final and time initial. Okay. All right, so with that said, for the very first acceleration, for the very first time interval here, which we said was between 0 and 5 seconds, okay, we have then a 5, let's go and do this, v final is going to be 5 meters per second minus v initial, which is 10 meters per second, all over 5 seconds minus 0 seconds, okay, t final minus t initial. Okay. And so therefore we see then we have a negative 1 meter per second squared acceleration. Okay. Make sure you're able to do that. Negative meaning here then, negative acceleration in this instance means slowing down. Even if we don't have the graph here, we know that it's slowing down because the velocities are positive and the acceleration is negative. Okay, so, but the graph really lays it out very clearly for us that the object is slowing down. But again, like I said, we can use the signs here for acceleration and the signs for velocity and not for time. Make sure you remember, you're not comparing acceleration to time, you're comparing acceleration to velocity here. So the velocities here are positive, the acceleration is negative, therefore then the object is slowing down. Okay, so real quick then, for the second acceleration time interval here, let's go ahead and work this one out, delta v over delta t. Okay, this is going to be v final minus v initial all over t final minus t initial, plugging in our numbers here then. Now it's going to be 0 meters per second. Okay. So what do we have here? minus 5 seconds, sorry. So t initial at this point is 5 seconds here. So we have 5 seconds, meters per second, over 10 seconds minus 5 seconds. Okay. And so with that said, then we also see that we have a negative 1 meter per second. Okay. Acceleration as well. Okay. So basically, we take the final velocity here, the initial velocity here. Okay, so we have final minus initial. The time interval here is from 10 seconds to 5 seconds. So we get then a negative 1 meter per second acceleration as well. And so in this case, then we have constant non-zero acceleration. So the acceleration is constant. Okay, and the acceleration is not zero. And I'm sorry, meters per second squared. Okay, is not 0 meters per second squared, which means then it continually changes its speed as we go all the way down to 0. So at any time interval between 0 and 10 seconds, it's constantly changing. It will have a different velocity at any moment in time between 0 and 10 seconds to the point where it eventually stops. Okay, and then at 0 seconds, 10 seconds here, it comes to a stop. Okay, and so that was what I was hoping that you were able to do yesterday on your paper. So I'm going to go ahead and I'll save this here. Okay. And so let's go ahead then. Let's take a look at a few drawings here and let's see what a few of you did. So Elijah was able to get this done. He did it for line D here. Okay, so he did it for object D. And so let's go ahead and analyze this really quickly. So thanks to Elijah for providing this for us. Okay. And so let's go ahead and let's take a look at what we have here. And so the object here is speeding up. So object here is speeding up. And so Elijah represents that with the different vector lines for acceleration, which is absolutely good, very good. So with the acceleration, first acceleration here, it's going to be less than the second acceleration here, which is going to be less than the third acceleration here, okay? All right, so the issue now is this, okay? Is the acceleration changing? So what Elijah has pointed out for here is that the acceleration is changing. Now remember, this is velocity versus time. So the velocity is changing, but the acceleration is not. So I think I commend Elijah for doing this, but I think what he did here was instead of indicating acceleration, this should be velocity. Okay? So the velocity is increasing. So velocity at 1, velocity at 2, and velocity at 3. So we're not dealing with a change in acceleration. We don't deal with that in this particular class. Okay? We'll deal with that. You deal with that more in physics. Okay? But what we have here is actually a change in velocity, whereas velocity 1 is going to be less than velocity 2, which is less than the velocity 3. So what we have here is a change in the velocity rather than a change in the acceleration. Okay, so the velocity changes. Okay, but with that said, then the acceleration doesn't change, but it is constant. It is constant. So the acceleration here is constant. That means you have a acceleration that it doesn't change, but you do have an acceleration that is constant and not zero. It's constant, non-zero acceleration, which means then that this object will continue to have a different velocity. So as we move from one time interval here, so we can call this t is equal to 0, t is equal to 1, t is equal to 2, t is equal to 3. So make sure you indicate the time intervals as well. Okay. So as the time interval increases, and we want to make sure that we look at equal time intervals here. So each time interval is equal. The velocity is going to change with each time. Okay, with the time here. And so with that said, then whatever the velocity is here at times equal to 4 seconds, it will be different. So the velocities will never be the same. The velocities will never be the same. And as we move outward here, the velocity is going to increase, which means then that this object is speeding up. Good. So the object is increasing over time. So that's very good. Okay. Object is increasing over time for a couple reasons. We have a positive slope. Is positive slope or a graph. But furthermore, what you're going to notice here then, if the slope is positive, acceleration is going to be positive. And if you notice here, the velocities will always be positive. So both the acceleration and the velocity have the same time. That's how we also know that the object D here is increasing in speed. It's increasing in speed over time. So very good. So Elijah got that right. And so with that said then, hopefully you recognize here that the initial velocity, since we're choosing object D here, the initial velocity here is going to be 0 meters per second. Okay? Now, Question I'd like to ask you then is, where do we find D at the end of this interval here? So real quick on your paper, I would like to answer this question here. Okay, I'd like to answer the question, and the question I'm asking you using Elijah's graph here. Where is object D at the end of the time interval that we're looking at here? It's at the end of the time interval. So on your paper, sorry, let me erase that real quickly. The question I want to ask you, and please answer this on your paper, at the end of the time interval, where do we find D at the end of that time interval? At the end point here, where everyone here, where do we find D? So go ahead, real quick, jot down your answer, a few words, and then we'll go over it okay? Go ahead and write down your answer. All right. The answer is, where do we find D? We don't know. Okay, so the answer to the question is that we do not know. We don't know. And the reason for that, folks, is because this is a velocity time graph. Position cannot be obtained from a velocity time graph. So position cannot be obtained, and let me just add to this and then sorry, folks. You cannot obtain information about velocity time graph, position from obtained from, position cannot be obtained from a velocity time graph, okay? All right, so that's what you need to remember. Any information about position, actual positions, or even relative positions cannot be obtained here. We don't know at the end if D is in front of A or D is behind B or C. That we don't know. Okay, we cannot obtain that information from a velocity time graph. We just know then at the end here, D is moving faster than A, but it's moving slower than B and C. That's all we know at the end of this time interval. And we don't even know the actual speeds because it's not labeled here on the axis. Okay, all we know from here, all we know from this then is at the end of this time interval here, D is moving faster than A, but moving slower than B and C. Okay, so make sure you remember this part here. And again, I'll be asking you this question quite a bit because it's going to come up. It's a very commonly made mistake for students of physics, students new to physics. Okay? All right. So thank you to Elijah for providing that for us. Let's go ahead and let's take a look at the next one. Melissa deals with object C, and quite a few of you dealt with the movement of object C here. And so let's go ahead and take a look at how Melissa interpreted the object C here and how object C moves. Okay. All right, so object C here, let's go ahead, and Melissa points out then that the object starts out, and she said arbitrarily that it has velocity of 10 meters per second here at time 0, okay? And so at 2 seconds in, Melissa indicates then that the velocity is still 10 meters per second, and as we can continue on, at 4 seconds into this observation here, we have the velocity of the object still at 10 meters per second. Is that correct? Absolutely. Okay. So if we're looking at this here, and Melissa's calling this point here 10 meters per second, sorry, 10 meters. Okay. Okay. Melissa's pointing out then at this point here, at this point on the graph here, that this is 10 meters per second. The line, the slope here, the slope for this object is 0. It has 0 slope. There is no slope here. And so therefore, if the slope is 0, remember slope on a velocity time graph gives us acceleration. The acceleration will also be 0, okay? Okay. And if the acceleration is 0, the velocity doesn't change. And that's exactly what Melissa has provided for us here, okay? So she indicates here very clearly that the velocity doesn't change, which corresponds to this this line right here, okay, corresponds to that line. And then furthermore, so we can get that information from the graph. And furthermore, Melissa calculated the acceleration for us, and which is absolutely right, okay? So acceleration, remember, is going to be the change in velocity over the change in time, okay, which is going to be v final minus v initial over t final minus t initial. And so in this case, then Melissa showed then that we're looking at the time interval between 0 and 2 seconds. Okay, and so therefore, she plugged in the numbers here. That's t final, that's v final, that's v initial, and that's t initial. V final and v initial are exactly the same, and so therefore the change in velocity is going to be 0 meters per second. Okay, and if the change in the velocity is 0 meters per second, the acceleration, that will always mean then that the acceleration will also be 0. Okay, and so the 0 change in velocity, that means in the velocity final. And what does change velocity equal to 0 mean? It means in that v final and v initial are exactly the same. They are equal to one another. Okay, that does not mean, again, when the change in velocity equals 0, when the acceleration is equal to 0, that does not mean that the velocity is 0. It does not mean that the objects come to a stop. It simply means then that the final and initial velocity are both the same. So does that, if an object is not moving, does that mean it has no acceleration? Well, it only means it has no acceleration if it stays not moving. So if it stays at a standstill, okay, then the acceleration will be 0. And in that case, then the velocity, an object at rest will have no acceleration. However, and the reverse though is not true. An object that has no acceleration does not necessarily mean that it is stopped, that it is at rest. Okay, so you want to make sure you keep that in mind. Okay, so very good. This is the absolute. This is how you should be able to interpret the graph here for object C, and that's exactly what Melissa did. So very good, Melissa. Thank you for providing us with that work there. Okay, and you got it absolutely correct. Okay. All right, let's go ahead and let's take a look at another one of your classmates' contribution. Okay, and let's take a look at what Lucas has provided for us here. Okay, so Lucas also has chosen object C here. Okay, so we have V final, V initial here, and Lucas here clearly, without plugging in any numbers, he clearly indicates here then that V final, V initial throughout any time interval here, throughout any time interval is going to be the same, and so therefore the change in velocity is going to be 0, and he shows us here also that if the change in velocity is 0, if you plug it into the calculation here, where we have delta V is over delta T, if that's the case, then that the velocity then is also going, the acceleration will also be 0 meters per second. Okay? And so he points out here that it's constant velocity, 0 acceleration, so that's absolutely correct. Okay, so without using any numbers and just interpreting the graph here in terms of simple equations, you see that happening as well. Okay, so absolutely. So the way that Lucas interpreted this graph here is absolutely correct, and so very good. So thank you to Lucas for contributing that. And again, the difference between Lucas's contribution here and Melissa's contribution, both of them reached the same conclusion. Both of them presented their argument very well. Okay. The difference here is that Melissa chose to use numbers and Lucas here chose to use equations here. Both are perfectly acceptable. Okay, and that's the way that you should go about doing it. Okay. Very good. So thank you to Lucas for that contribution. Okay, let's go ahead and let's take a look at one more. Let's take a look at one more and let's see what we have here. So let's take a look at what Jolene did. And Jolene also chose to analyze object C here. And so Jolene did the same thing with that Melissa did. Okay, so she did the same thing. She indicated here that initial velocity is 0. So make sure you understand that the initial velocity at time 0 is not 0 because object C starts out up here. So very good. So she indicates then that it's not equal to 0. She indicates 2 time intervals, T1 and T2. Now, she also indicates here that, and I think the symbol here is the only thing that I would suggest you change your Julian. That is the units are for acceleration. So therefore, this is acceleration in time interval 1, and the acceleration in time interval 2 is going to be 0 meters per second. Okay, so not the velocity. Remember, velocity meaning then that's how fast it moves. This is acceleration here. Okay, so the acceleration is 0 meters per second, which means then there is no acceleration throughout this the first second, and there's no acceleration throughout the second here. Okay, and so Julian here again, she chose to use numbers here, which is very good. Okay, and this worked out very well as well. Okay, so the only thing I would be cautious about here, Julian, is just using the correct variable to represent it. Okay. All right, so very good. So the contributors, so I really appreciate those folks who contributed here, and you really gave us a chance to analyze the work and look at your thinking. Okay, and so this is what we all should be able to do. This is what we all should be able to do. And so what I would like you to do then is, if you have not yet drawn these diagrams here, I would like you to do it, and then I'd like you to submit it. Okay, therefore, if so, take a look at your work that you did yesterday. Okay, so on your paper today. Okay, if you did not do it yet, if you did it already, just make sure you write on your paper that you've already done it. Okay, and then I'll go back and I'll check. But if you have not done this yet, if you have not done this analysis yet, if you didn't do it yesterday, I would like you to do it today. Okay, so make sure you include it on the work that you submit for today, and that way then I can take a look at it. And if you have any questions about it, come by and see me, and we can analyze your diagram much the same way that we analyze the 4 diagrams here. Okay, so again, please make sure you get it done. I'd like to see how you interpret this graph here, and then come by and see me on Monday. I'd like to get started on a couple of calculations. Okay, we're going to use the equation for acceleration, and then based on that, we're going to get into our first kinematic equation that we're going to look at. Okay, so we'll start the kinematics. We'll finish up with the hopefully with one-dimensional kinematics tomorrow, and then Monday we'll start that. Okay, we'll look at the kinematic equations, and hopefully by the end of next week we can, by the end of next week, we can go ahead and start two-dimensional motion, specifically projectile motion. Okay. All right, folks. Well, have a good weekend. If you stop by after school today, if you have any questions, but if not, I will see you on Monday. Okay. Have a good weekend.